My name's Raymond, Jett. I run Arcadecomponents.com. I started this company back in 2005 because I had a pole position arcade game board that didn't work. It had a RAM error, and I needed some 2149 RAMs. And there I go with my phone. This is the reminder that we should have our phones on stun. Well, if my phone wants to respond to the buttons, tell you what, I'll just say power off. He was trying to call me, Jay, so. All right, so 2149 RAMs, couldn't find them. Went to First Saturday, found a 16-bit MFM card, and it had two 2149s on it. Went home, desoldered them, put them into pole position, and was playing the game in about 10 minutes. So I figured if I had a hard enough time finding parts, so would other people. So that's when I started it. Today we're going to talk about digital basics. You know, if you want to learn how to repair something, you really need to understand how some of it works. So I've got another session where we're going to go over computer circuit basics, where we're going to talk about clock circuits, reset circuits, address decoding, all the little magical stuff that your computer does. But this, we're going to get into the even more basics. We're going to look at the logic chips that help make this up and understand a bit more about the very basics of everything. So we're going to talk about binary and defining zeros and ones. You know, because a computer, that's all it cares about, zeros and ones and groups of zeros and ones. We see it as assembly language. We see it as high-level languages. We see things, but computer, all it sees are zeros and ones. We're talking about some basic logic gates, power supply noise and how that can affect your logic gates. We're going to look at some bigger logic gates, you know, like some like 74LS138 3 to 8 decoder. Yeah, I know that off the top of my head. Considerations, because that's one thing people say, it's a 7400, but all I have is a 74LS00. Will it work? Well, the answer is maybe. And then we're going to talk about issues with what we call logic state, which affects how you measure things. So why are we here? You know, learn the basics, to understand more about these things that we love and want to learn more about, you know, like how to repair, how to maintain things. There's a concept called truth tables when you're dealing with digital logic. It's a little table that tells you the goes intas and the resulting goes outas of the chip. And understanding the truth table makes it very much easier how to understand it when you get to more complex chips. So we're going to look at the truth tables from the simple ones and on to the more complex ones. So at the end of this, you should be able to count to 16 in binary. Yeah, maybe a little bit further. It depends on how far you want to go. But yeah, if you start here and that's 0, that's 1. 2 is actually that, so you know, just be careful counting if you're in school and somebody's like, ooh, or somebody at work takes offense. We're going to look at the basic logic chips, understanding how that logic state can impact your troubleshooting. And when I say logic state, I'm not talking about the state of a 0 or a 1. I'm talking about the state of a relationship of an input to an output of the chip. And we'll get to that. So base 10. You know, that's what we count in. Computers count in on or off, a 0 or a 1, which is binary. So when we talk about base 10, you know, we go 1 through 9, and then we carry a number over to the next space. And as we run out of fingers, you know, we have to move to toes, you know, get to the next number. And you could look at this as counting in powers of 10. So 10 to the 0, that's your 1 space. 10 to the ones, your 10s, 10 to the 2s, 100s, 10 to the third power is 1,000, and so on and so forth as you move this way. Now, when you're dealing with binary, you're dealing with 2s. So it's 2 to the 0. When you put that in your calculator, 2 to the 0 is 1. So you have 0 and 1 when you have 2 to the 0. That's how many different combinations you can have for that. 2 to the 2, that's 2 times 2, that's 4. So when you have 2 times 2, you have 4 different numbers here. Now you might say, wait a second, 1 and 1 is 3. How do you get 4 numbers? Don't forget 0 is a number. So it's 0, 1, 2, 3. So that's 4 different combinations that you can have for that one. It's 0, 1, 2, and 3. And you just keep going further and further. You just add an O. So it's 2 to the 0. That should be 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. Yay, I get to fix the slide. And so we call this base 2 because there's only 2 representations, whereas we count in 10, so it's 0 through 9. You know, we add another number, we have to move over a step, put a 1, then we have 1, 0, 10. So that goes back to the old joke. There are 10 types of people who understand binary. All right, so logic levels are binary. They're on or an off, a 0 or a 1. So that's why we represent it as simply a 0 and a 1, but that's not quite the case of being a specific voltage level. There's a range of it. So when you look at it, they say, okay, anything from 2.0 volts and up is considered a logic high on input. Anything from 0.8 down is considered a logic low on input. What's the area in between? No man's land, indeterminate. There's not a logic state there. Now on the outputs, they try to drive it to 2.4 and above and 0.4 and below. Now why would you drive the output higher?
Voltage loss.
Voltage loss. You know, your traces have a bit of resistance in them, and you have some loading of the circuit with the different chips you're driving from that output. So they try to drive the output a little bit higher to make sure that when it gets to the other side, you know, you meet that 2.0. But typically when you look, you'll see it's typically like 4.5 volts and up. But that's the range. So truth tables. You look at this and you're like, what the heck? But it's really simple. So if we look at this one, if this is low, the output's low. If this is low, the output's low. The X means I don't care what this level is. If this is low, the output's low. This one and this one are high, the output's high. What do you think this one would be called?
AND gate.
An AND gate. If this and this are high, the output is high. So that's where we get and or not, you know, the different gates. This one is a little bit more complex. You have some enable lines, okay? If the enable lines, if this enable is high, then we can process it. If this output is low, or input is low, then we have the different selects and the different outputs. So how many combinations do we have here since we have 3 lines?
That's like 30.
Think in binary.
That's 16. No, 8.
That's
Yeah.
8.
It's 8. 2 to the 1, 2 to the 2, 2 to the 3. 2 times 2 is 4, times 2 is 8. So if you think of it in binary, it's 0, 1, 2, 3, 4, 5, 6, 7. So 0 through 7, 8 combinations. The enable lines just say, okay, these are conditions you have to set to enable this to output here. So all this is doing is you have 8 outputs. When you have the combination from 0 through 8, or 0 through 7, then you have one of these outputs going low, depending on the number you give it.
That's a decoder.
LS138?
Yes, 74 LS138, 3 to 8 decoder.
Yeah.
So if you look at the 8031 show kit computer that I have out for sale in my booth, you'll notice that it has a 74 LS138 on it, and that's for the ROM space. The 8031 CPU and its related families are a little different because they have 64K of ROM space, 64K of address space. So on the ROM space, the LS138 decodes it so you have 8 blocks of, how many K do you think? You have 64K of memory space. 8 blocks of 8K because we're taking address lines A13, A14, and A15, the top 3. So we're decoding those and saying that from 0 to 8K is here, 8K to 16K is here, 16 to 24, 24 to 32, so on and so forth. So you learn a little bit about address decoding while learning a little bit about logic and truth tables. So with this helps you understand that, you know, this is how these truth tables work. We give you a set of conditions, and with that you have these expected outputs. So looking at a basic gate, a buffer. Buffers are used to increase drive of something. You know, so you'll see a lot of these on CPU boards but they'll be packaged in multiples with 8 of them on a chip. So that you have 8 of your address lines going through one, 8 going through another. All that does helps you to improve the drive capability. So if you have a lot of chips that are sitting on that address bus, you're sending it out this way, and it's helping to get that signal, stronger signal out that you can drive for more inputs of other chips. Why wouldn't you use that on a data bus?
Bidirectional.
It's not bidirectional, it's unidirectional. You have one goes into, one goes out to. So it's a one-way street. But if you look at the function table, the input's low, the output's low. Input's high, output's high. Now we can look at the concept of bubbles. What the heck are bubbles? Just think of bubbles as not. Bubbles are an inversion. So we look at this is an inverter. This just simply says if the input's high, the output's low. The input's low, the output's high. You'll see a lot of these in reset circuits, clock circuits, and other places where they need to invert a signal to do some kind of control. Like on arcade games, you'll see this where in the clocking circuit, you'll have a clock that says this is 1H. So it represents one horizontal line. And then you'll see one that says not 1H, where they run it through an inverter. So it's the opposite of that signal. This symbol right here, we'll look at here in a little bit. That is a special symbol that has some significance into how the gate operates. It's still an inverter. It still operates this way, but we'll get into that shortly. That's an interesting symbol. Now we look at AND gates. This is the symbol for the AND gate. Inputs, I don't care what this is. If this is low, the output's low. Same thing here. I don't care what this is. If this is low, the output's low. If this is high and this is high, the output will be high. So it's real simple when you're doing the small logic gates that they're easy to follow. They get a little bit harder to follow when you have them all strung together and you have to figure, okay, how are they adding this signal in, subtracting this signal out? But the NAND gate is the next one. Think of this as an AND gate, but you're inverting the output. I don't care what this one is. If this is low, the output's high. If both inputs are high, the output's low. So you're just inverting the output of the AND gate. Remember the bubble. And then we have the OR gate. If this one's high or this one's high, the output's high. If they're both low, the output's low. And then we have a NOR gate. So think of it as an OR with an inversion at the end. So we have, if this one's low and this one's low, the output's high. If either of them are high, the output's low. It's not difficult concept, it's simple, but it's just having it explained and looking through the truth tables, understanding how those operate. As you learn these and how they work, as you get to more and more complex chip, that breaks it down for you, makes it so much easier to understand how the more complex chips operate. Now this one's an interesting one, an exclusive OR. Now the exclusive OR, the typical design drawing for this is going to be this one. This is pretty much the modern one. But when you look at old schematics, they could draw it in multiple ways. But they have that second line back there. So it can be a little bit confusing when you're looking at old schematics for things, which, let's face it, we're all into old computers. So you're going to find old schematics out there. Now with this one is the output is high only if A or B is high. So if they're both high, the output's low. So it's exclusive only if one is high. That's where we get the exclusive OR from. You'll see this a lot in sync circuits, where they take the horizontal sync and the vertical sync together to combine to a composite sync signal. Because what do our monitors take? They're TVs. What do they take? Composite sync. Even if you have RGB and you have RGBS, it's RGB and a composite sync. Or if you have sync on green, it's red, blue, and a green with a composite sync signal superimposed on it. So if you have a vertical sync missing and it's constantly rolling, check that combiner, check that exclusive OR gate to see, are we getting the correct output based off the inputs, or is that input missing? If the input's missing, track further back in the circuit to find the next gate back that's supposed to be driving it and see if its input's missing. If its input's missing, go back further in the circuit, the next gate, and if its input's there and its output's missing, replace it. So all we're doing is just stepping backwards through the logic as we troubleshoot. Now, effects of power supply noise. When you have a noisy power supply, your logic isn't looking smooth. It's going to have some jagged looks to it. It's going to have some ripple on it. You'll see the flats on it will be like this, on your oscilloscope. But that can cause a problem when you get to that transition point where you're in that no man's land and you're transitioning between logic low and logic high, that it can cause it to bounce that output and you get extra little pulses that you don't want. Now, how do we fix that? How do we address that? Come on, it's a popular thing. You buy a kit in the mail. Yeah, you recap it. If your power supply is old, you may need to recap it. If you have capacitors on the board, look at them to see if they need to be replaced, like if they're electrolytics, if they're a bunch of ceramic caps that have just been knocked off and missing a leg, you replace them. When you're dealing with the capacitors, the bigger capacitors filter what? The lower frequencies. And the little 0.1 microfarads that you see all over the board, what do?
High frequencies.
The high frequencies. When chips pull current, they pull it in high frequency bursts. And that can cause hash and trash noise on your plus 5 volt line. That's why you have all those little decoupling capacitors all over the board. And it can make a difference in how things run. I built a Leningrad 128, which is a Spectrum clone, and they don't believe in decoupling capacitors. So I had to go find all the little vias where 5 volts were, and all the vias where ground were, and put decoupling caps wherever I could around the board to stabilize things. All right, so let's get into some advanced logic gates. 74LS244. Octal buffer and line driver. This is the chip I said that you would see on address lines. Octal meaning 8 logic gates, or eight logic gates in that package. But you also have some other gates that are driving the enable lines, because this one is a little bit different, because you have an enable. If the enable is high, we have an X. We don't care. But what does the Z mean?
High impedance.
Yes. High impedance. That means the chip goes hands off the bus. It goes high impedance. So it doesn't represent a load, an input load or an output load on the bus.
Kind of like a disconnect.
Yeah, kind of like a disconnect. Yeah. And so we have also this bar over this G. What does that bar mean?
Active low.
Active low signal, a NOT. And you can see that with the bubble on the drawing. This, where do you find the truth table and these little drawings?
Data sheet.
Data sheets. Data sheets are your friend.
Big yellow book.
Big yellow book. Or if you're in my shop, on the back of the bench, I've got a 42-inch monitor on each of my 2 main benches tied to a little PC that I just go out to a website that you'll want to learn. It's datasheetarchive.com. And you go out and you punch in the number of the chip and you pull up the data sheet. Does it matter what manufacturer when you're dealing with a 7400 series logic chip? No, not really. Just make sure you get the correct family type. Are they all the same pinouts across family types?
No.
No.
There was somebody redoing a computer space game and having problems because he had an LS chip which had an edge clock instead of a level clock on a
Yes.
flip-flop.
And you run into things like 74L86 being a different pinout than a 74LS86. Or a 54LS74 having a different pinout than a 74LS74. Generally, they're the same pinout, but if you replace it and you're like, this doesn't make sense, check the data sheet. Make sure the part you're putting in is the same pinout. Now, what's the difference between an SN 7400 and an MC 7400?
Manufacturer.
Yeah. Who typically puts SN on their parts?
National Semiconductor.
Texas Instruments.
SN is NS, National Semiconductor. SN is TI.
Oh yeah.
And MC is Motorola Corporation. Now, you will find some Motorola that's marked SN74XX. That kind of blow your mind, but it does. You know, when dealing with second source and other things, you see some strange things. Like Motorola has MC2716 EEPROMs. Motorola also has TMS 2716 EEPROMs. What's the difference? Major headaches. That's the difference. The TMS 2716 was early to market. It uses 12 volts and minus 5 volts along with the plus 5 volts like the 2708s did. But Intel and everybody else decided we're going to go to 5 volt only parts. And so 2716 is a 5 volt only part.
I found some 64 megabit DRAMs once that needed minus 5. Fortunately, it was a color computer and I could just put one jumper the other way.
Data sheets are your friend. All right, so we have this right here. So if we bring this low, that enable pin low, then whatever we have here at A gets sent to B. If it's a low, the output's low. If it's high, the output's high. And like I said, you'll see these on the CPU buses, on the address bus. This is a Konami arcade game board, just a generic Konami board. I forget if this specific one is track and field or hypersports, but they have a Konami 1 CPU, which is their custom 6809 Motorola CPU core with a couple extra things added in. But here we have these grounded, the 1G and the 2G, the two enable lines grounded. What does that mean? When we ground those, it's always active. So whatever's on the goes into immediately goes to the goes outa. Now, with this, when it's always on, it makes it easy to spot when you have a signal missing on an output, because your inputs, like, you know, if you have a logic probe, always get a logic probe that has audio beep functionality. Why?
So you don't have to look at the screen and what you're doing at the same time.
Kind of.
Okay.
Catch those quick ones.
The audio pulses, the sounds will tell you things that you can't derive from subtle little changes in how the light operates. The audio is a lot clearer. So if you're over here and you're probing this and you get a beetle, 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 and over here you get beep, beep, you got a problem. Or if over here you have beep, 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 and over here you got like a motorboat, you got a racing output on the chip. So the audio can tell you things that you're not going to easily see through the lights on that. And the logic probe is the absolute, by far, #1 tool I use when troubleshooting arcade game boards and old computers. Now, may require a logic analyzer or replacement of the chip if the outputs are kind of noisy. When I say noisy, you'll put the probe on this side and you'll hear beetle, 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 and you put it on this side, you hear. That could be perfectly good signal. It's just that that's the only thing driving it. Other times, you'll hear the same beetle, beetle on the output because you'll see there'll be some resistor packs over here tying the output high, and that helps. But when there's no resistor packs and this is the only thing driving it, you'll hear just only the signals coming out of this, and it may sound a little scratchy. The only way to 100% know for sure if everything's correct is to look through it with an oscilloscope or a logic analyzer. Now, what's the benefit of a logic analyzer over an oscilloscope?
Small, fast, easy to set up.
Multiple lines.
Multiple lines, which you can see. Oscilloscope, you're limited by how many channels you have on that oscilloscope. You have a single channel oscilloscope, you can check the input and an output of an inverter. If you have a logic probe, you can check the input and the output of the inverter. But you can't check both at the same time to see that the input is matching the output. Or in the case of the inverter, it's opposite. The logic analyzer gives you more input. So when you're dealing with a chip that has 20 pins, then you can see what's happening across the whole chip all at once. You can see the inputs as it relates to the output on each channel. And we'll talk more about that when we get to the state. Next one's an 74LS245 octal bus transceiver. Transceiver as it sounds, transmit, receive. With this one we have a direction pin that says which way do we send the signal, and then we have the output enable. Now with this one, if the output enable is low, because it's got the bar over it, the chip is active. Direction, if it's low, we say let's copy whatever we see on the B data bus to the A data bus. So from here to there. If it's high, then we copy from the A bus to the B bus. You see this a lot on your data bus connections. It goes from CPU directly to the 74LS245, and then you'll have your read and write functions controlling the directions.
Question. The line that's coming in on the top of the triangle is considered an input on those?
Which one? This one?
Yeah.
That's your control line. So you got your direction here, and you've got your output enable here. So with these, you're combining those signals and sending it down here, and that controls those gates. So if you have this direction low, and we go from B to A, then this gate is disabled, this one's enabled, and the signal goes this way.
Right, but what I meant, if you were just looking at that by itself in the truth table, that would be considered an input to that.
It's an input to the gate, but it's a control input, not a data input.
Right. And so that's why it's represented on the top.
Yes.
Oh, thank you.
Oh, yeah. What's on that?
Now, what is that symbol? That represents what we call a Schmidt trigger. Now, the cool thing about Schmidt triggers is if you have an analog signal coming in, you need to square it up. You'll see this on light gun games. You get the light gun signal coming in, they'll feed it through a 74, typically an HC14, but you can use an LS14. It squares up that signal, the slow rising signal, real fast. But what it does is it keeps track of, we get the logic high and the logic low state, we got the indeterminate. So what happens here is instead of every time we get into some indeterminate area, we start switching signals back and forth, ending in extra pulses we don't want, we snap. We say, okay, this is low until we reach high, snap this immediately up high, and then when we get to the low, we'll snap it down low, and in the intermediate area, we're gonna stay. So it just, wait for it, now. Wait for it, now. It just takes immediate action and it squares up that signal. So it keeps you from having all that extra garbage in there.
So input signal could be two different states, just depending on what preceded it.
Well,
In the indeterminate.
where are you going with?
I guess I'm saying like the light fades on. Let's say as you move this light gun around, it fades on and the voltage stays high until it gets.
It reaches down to the point where we would
Yeah.
consider it a logic low, and then suddenly,
Yeah.
boom, it's down.
Okay.
Yeah, rather than bouncing like that. And so the bus transceiver, like I said, sits there in the data bus because it's bidirectional. We don't use them on address buses because we don't need them on address buses. Because you address bus, you're never telling the CPU, hey, here's A15, Mr. CPU. The CPU's saying, no, I want to access this memory. I'm going to raise A15. Now, this one can be, again, difficult to troubleshoot without using a logic analyzer, just simply because the signals are moving so fast and you have the control signals going into it. It's possible that everything looks good, but maybe you have a racing output that's hard to detect because the CPU is operating really fast as well, and you're getting some invalid logic states coming in, data states coming into that CPU. So sometimes it's easier to troubleshoot these by just yoink and putting in a new one. Now this one's represented a little bit more difficult. This one you have a little arrow on the input. What does that arrow mean?
Rising edge.
Rising clock edge. Yeah, because that's our clock that we're using. And then we have a clear. So with this one is a 74LS273. This one is used to latch data from an input to an output. You will see on the 8031 kit that's at my booth that it has a 74LS573. Similar function. The difference is that, look at the pin numbers. You have an input on 3, an output on 2. Input on 4, output on 5. What do you think that does to routing traces on a circuit board? When you have inputs and outputs going to next pins on the chip. The 74LS573 has inputs all on one side, outputs all on the other side. Makes it much easier to route your traces on a circuit board. You can make things more tighter, more compact. So, but what this is doing is, on that computer, it's used to latch the address lines because that CPU multiplexes them. You'll find this on 8085 CPUs as well from Intel, where you have a multiplexed address and data bus. So the first low 8 bits of the address bus is also the data bus. And the upper bits are separate, they're only address. So you have an address latch enable signal that you will send out here to the clock. So that when that is asserted, then you're going to send that data from one side to the other on the rising clock signal. You'll see these chips. This is a fun chip because you can do so much with it. Not only can you do that with it, but you can also do things like output video. You'll see this on a lot of different systems where you have RGB outputs because they'll take the video data and then they'll output it to resistors as a kind of a poor man's ladder DAC, digital analog converter, driving some transistors, and then you drive your red, green, and blue outputs. Really slick. And there goes stuff off the whiteboard. We talked about the 74LS138 earlier. We looked at its truth table. Here's the pinout of it. We have an A, B, and C. Those are our 3 select lines. Then we get the G1, G2, A, and G2B. Now, if you look up here, they just call that G2 asterisk because they're talking about it being G2A and G2B combined because they both have to be at the same state for that to happen. So they give you a couple of extra things here that you can use so you can further decode things down. Like say you can run address lines, 12, 11, and 10 here and put 13, 14, 15 here. So they have to be in a certain state before you decode this to get it down further into that area of memory you want to map into. Typically, you'll see something like that, or you'll see another signal coming in here that says, okay, if this one goes high and these two will be tied to ground, then based on this condition, we're doing one of these. So you might see that in something that is activating a sound circuit. You have separate different analog sound circuits. You want to enable one at a time so that you can trigger off the sounds. The use of this is just limited by your imagination on what you think you can do with the set of input controls and what you want to drive with the outputs.
What's the purpose of offering 2 pins for when you're going to interpret them the same, or you're going to require them to be the same, like the G2 NAND?
Well, you have 2 separate signals coming into it that you want to use as triggers that you don't have to combine with another gate like an AND gate to bring it down to 1 to drive that. So having 2 gives you more flexibility for that, and if you only need 1, then you just tie this one to ground. So you'll see a lot of this and its companion 74LS139, which is a 2 to 4 decoder. 2 input pins, 4 output pins. So remember your binary, 0, 1, 2, and 3. It gives you 4 different states so that you can drive one of those 4 output pins to enable something. Those are common ones that you'll find in a lot of computers used for address decoding. We'll get further into address decoding in my other session. And you'll see that this is used, like I said, on the 8031 show computer. This is actually from the schematic on that. So we ground G2A, G2B. We tied G1 to 5 volts. So whatever is on A 13, 14, and 15, we decode. And so these are your address ranges from 0 to 1 FFF, which is from 0 to 8,191. Then that's from 8,192 to 16,383, or 2,000 to 3FFF. Now when I say 3FFF, what is that? Hexadecimal. Because computers count in, and you represent a group of 4 bits as hexadecimal. It's 0 to 15, 16 different values. It makes it easier for humans to understand the computer stuff. Because it's a lot easier to remember 0 to 1 FFF than it is 0 to 8191. And it's easier to work with hexadecimal when you're dealing with this. And when you say a value of something is FF, what is that? 255, which is the maximum value in how many bits?
8.
8 bits, because F is
16.
F and F. Now you have all ones, so that's 256 values that you could have in binary. But remember, zeros and numbers, so the top number is 255. Because when you reach 256, it's like getting to 9, you have to carry over. So that's a real world application for the 74LS138. Now, when replacing chips, can you use a different family? Yes and no. The yes is, it generally works. The no is that some of them have a slightly different value in what they represent as the triggers for a logic low versus a logic high, and what their outputs are for that logic high. So we have, this is what it expects on the input, all of them expect 2, but the drive output's a little higher on some of the others, like the 74S and the 74LS is a little bit higher. And same on the output, what they consider low on the output and what they consider low on the input. Now, that's not really the biggest difference on this. The biggest difference is going to be speed and delay. So some of the things are actually faster speeds. So you got 54H, H for high speed. You got low power Schottky, low power. Over here we have Schottky, which is going to be high speed. Advanced Schottky's high speed. Advanced low power Schottky. It's going to be really fast as well. 74F is considered 74 fast. If you're doing a 74L, they're not going to be particularly really fast. The Schottky is going to be sharper inputs and outputs and faster on transitioning. When you transition from a 0 to 1, these things matter in some circuits because the tolerance is so tight that if you put a too fast chip or too slow chip in, it doesn't work right. Go back to that Leningrad 128, that Spectrum clone that I built. Column 32 of text was missing. So I had to play around with some of the different logic families to find a combination that would work, and I would get the text on the 32nd column. But then I looked and it's like, there's no color. So then I play with a couple of families on a couple other chips to get the color on the 32nd column. So yeah, sometimes that does matter on the speed differences and the delay characteristics of those. Now, when replacing them, can I use a different family? The answer is a little bit more complex because it really just depends on the circuit. Because you have fan-out capabilities like the 74AS and 54AS. You're going to use those. You're going to replace them like for like. You're not going to replace those with a 74LS unless what? It's a pretty simple circuit, because what does fan out mean? Anybody?
Connected to more than one circuit or multiple circuits?
No, what did I hear over here?
How much you can drive.
How much you can drive. So fan out means how many inputs can I drive with this output? So if you have a bus that has a lot of chips attached to it, the more chips you have attached to it, you got to be careful of that fan out. And that's when you start looking at, okay, which family can I use? I have a 74 LS here. It can drive up to 20 gates. You know, I'm not going to use a 7400 to replace it. I'll use a 74 LS. I could probably use a 74S or 54 LS. AS should work as long as the timing isn't violated for the circuit. So the answer is, it depends. What I would do is, if that's what I had, I would try it in the circuit and see. Now, logic state. When we talk about logic state in troubleshooting, we're not talking about a 0 or a 1 or the voltage levels of 0 and 1. We're talking about relationship of signals, inputs to outputs. And this can be a little bit difficult to determine with different tools. So logic probe, we can only see one signal at a time. So if this beeps, and they're beeping at the same time, then the outputs are going to go high at the same time. But what happens if we have a condition where they're slightly out of phase with each other? You'll see this a lot when combining circuits with AND gates, that you'll have beep, 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 beep. But out here you'll have beep, 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 different sounds, because you have different shaped waveforms coming out, because they're only high at the same time for a short period of time. That can be difficult to measure with a logic probe, because you're only seeing what's happening on one pin at a time. How many channels of an oscilloscope would you have to see the inputs and outputs on that? How many 3-channel oscilloscopes do you see on the market? So you're probably going to have a what? 4-channel scope. But yeah, you do need 3 inputs to be able to see what's happening as the relationship of the signals going into and coming out of that logic gate. So that's something to keep in mind when troubleshooting, that the tools that you have can have an impact on what you're doing on your system. Now we see that they're totally out of phase, 180 degrees out, then you'll see nothing on the output of that AND gate. But yet the AND gate's operating perfectly. It's just that when you're troubleshooting it, you can't tell what's happening here with just the logic probe. Now, having more inputs helps. More power. So, logic analyzer. This is an output from a logic analyzer I bought off Amazon, a little 16-channel. I think I paid $130 for it like 5 years ago. Excellent tools to have. You can buy them dirt cheap. The ones I would stay away from are the $8 Sele clones, just simply because the software to run those, you got to go find old versions of different software and different drivers to make them work, and it's a real headache. But hey, if that's all you can afford and you got time to go through and figure out all the drivers and stuff, go for it. It's a neat tool. And those little cheapy ones will do enough to be able to see what's going on with the AND gates and various things. But here you'll see the inputs and you'll see the outputs as they're related to each other as the signal keeps going until you run out of input buffer RAM on your logic analyzer, where it stores all those state changes. But this is neat because you can see if there's noisy outputs, if there's no output, if the output's racing. And when I say racing, it's just oscillating on its own. So you would see steady stream of pulses here, and an ungodly amount of pulses going across here. So here we can see what happens when they're in phase, in sync. Now here we can see what's happening when they're 90 degrees out of sync. And so we can see that the pulses are narrower because they're only combined, they're only high at the same time for a short period of time. Anybody remember Tanner Electronics? Love that store. They had for a while these little gates that you could solder the pins to and pop them on your breadboard and test. So made for great building of slides. They were excellent for learning basic logic. I don't know if anybody still sells those or not, but if you find some, grab them. So the logic analyzer is going to give us the full picture of what's going on. Now they're 180 degrees out of phase. So while this one's high, this one's low. We see the output's low. And with the logic probe, we're like, this gate looks dead. But it's not. It's operating properly, given the condition of the signals that's going into it. So I highly recommend tools. You know, it's where would we be if we didn't have an excuse to buy a new tool, new toy? They're cheap. You know, you can buy one of the little, like I said, Saley clones for $8 on Amazon. Tinker around with the software to get it to run, and you'll have fun with it. It's neat to see how everything runs, and you can, if you have something like a keyboard and you're watching the serial pulses of the keys, you can type different keys and you'll see the different pulses on there as the data is encoded going across. You can look at your USB ports and look at stuff, but that you're not going to catch a whole lot of because it goes through so fast you'll run out of RAM on the device. You know, the bigger the logic analyzer, the more RAM it's going to have, and the more of these state changes and things you'll be able to capture. So we learned to count in binary. Base what? Base 2. We talked about function tables. Talked about logic state as far as 0 and 1 and what the computer expects from a 0 and 1. Talked about power supply noise, how that can affect things. We talked about logic state in the terms of troubleshooting and how that can impact things. We talked about basic functions of chips that you'll find in your computers. Any questions over any of this? Andy?
There's no questions. I have something I think might be interesting. So you're talking about the AND gates. Let's say you want to make an edge detect. One thing you could do is take the signal, AND it with itself a couple of times to get that same signal back, but delayed a little bit, and then AND that with the original signal so that you'll just get a little pulse whenever it changes. So just to kind of like pull together some of the concepts you brought up.
Yeah, propagation delay. I think that's one you didn't specifically go over.
That
depends on.
That's the part where I didn't call that as propagation delay, but that's the part where you're dealing with different families and the different speeds that they operate in the circuit. The technical term for that is propagation delay.
Yeah. But that's what makes that work.
All right. Well, thank you for your time, everybody.